In this video, we're introducing vector calculus by having a look at some examples. In the first example, we're looking at how a particle's position changes over time and how we can explain that using calculus. So its position vector is described as 3i plus 2tj. So we'll substitute in some time values from 0 to 3 and see how its position varies. Now we know we can describe its position in terms of its components. Let's look at those components I and j for velocity, and we'll do that by differentiating. Now the derivative of 3 is just 0, so we'll put a 0i there. And the derivative of 2t is 2, so that gives us 2j. And that makes sense when we look at the graph. Horizontally there's no movement, but we can see vertically it's moving 2 units for every second. So given a position vector, we can differentiate each component, I and j, or k if we're dealing in 3 dimensions, with respect to t, and we'll end up with the velocity vector. Let's have a look at another equation for the position vector of a particle, and this time we'll determine the velocity straight away. So we differentiate each component. The I component gives us a derivative of 3, and the j component will be 2t. And once again what we'll do is we'll have a look at a position over time. So if we go back to our position equation, if we substitute t equals 0 into both of those parts, we end up with r is equal to 0i plus 0j. So this time we can see from the graph that the movement is not having a constant change each second. And if we have a look at the j component velocity, 2t, we know when we differentiate that, we're going to end up with 2 for the j component. Of course, the I component will be 0 for that derivative. So looking at it horizontally, the movement's constant. It's moving 3 units every second. But vertically, the movement is changing, it's increasing, so there is acceleration. Hence the acceleration is 2j, or just reflecting the j component. In this next question, we're being asked to work out the position vector. Now we're given a velocity, and we're also given a displacement at a certain time. Now we know from calculus that the displacement is the antiderivative or integral of velocity. So we can express the displacement equation, r at t, as equal to the integral of the expression for velocity. And in this case, we've got the integral of 2i plus 2j. Now when we anti-differentiate each part, we'll look at the I component first. We get 2t, and then j component likewise, we also get 2t, and we have a constant because it's an indefinite integral, but the constant is a vector. Now we're told from the question that the position vector at 0 is equal to 2j. So that must equal our antiderivative when we substitute t equals 0. And we'll do that for I and j components. And that means that our constant vector must equal 2j. We can now sub this back in for our integral or antiderivative, and we get that the position vector is equal to 2ti. And we'll combine the 2j for the constant with the 2tj that we had previously in our solution for the antiderivative. So it's 2t plus 2 for the j component. In this next question, we're having a look at a particle undergoing projectile motion. So whilst we'll consider that there's no effect horizontally to such things such as wind, we will assume that there is effect due to gravity which will pull the particle down. So let's draw a diagram, and we'll assume for the moment that the particle is leaving a position which we can label as the origin, and its path will be pulled down by gravity in this manner here, like a ball would be thrown from the air. And we can show its initial velocity with this dashed line. Now that's at 30 degrees to the horizontal, and it's moving at 20 meters per second. So we can use that to describe the initial velocity in terms of its I and j components. Now, working out the velocity, what we do know is that we have an acceleration, and that acceleration is due to gravity pulling it down. And we can anti-differentiate that to determine our velocity. So the acceleration is equal to negative 9.8, and that's a j component because it's pulling it down, and the units for that are meters per second per second. So if we anti-differentiate that, we can determine the velocity. And the antiderivative would be the integral of negative 9.8, of course a j component with respect to t, and we get negative 9.8t plus, and of course there's j component there too, plus a constant vector. Now we know that when t equals 0, the particle leaves the origin at 20 meters per second, and we can put that in terms of its I and j components. If we have a look at a triangle, what we can do is use the 30 degrees and also the 20, which is representing the hypotenuse in this case of our triangle, to break down the I and j components. Now the I component will be based on cosine, so it's 20 multiplied by cosine 30 degrees for the I component, and the j component likewise using the triangle will be based on sine 30 degrees. Based on exact values, we can simplify this because cosine 30 is root 3 on 2, and the sine of 30 degrees is a half, so a half of 20 is 10. So using that velocity at t equals 0, let's label our original antiderivative, and we'll substitute t equals 0 into that equation for the velocity, and we get negative 9.8 multiplied by 0 for the j component, plus our constant vector. Now we know that the velocity of 0 is equal to what we just found. We're simplifying the velocity to be 10 root 3i plus 10j, and that's got to equal 0j plus the constant. In other words, the constant vector is equal to 10 root 3i plus 10j. And we can substitute this back into our original integral where the asterisk is, and we get the velocity is equal to 10 root 3i, and we'll simplify the j components. It's going to be 10 minus 9.8t. And that's our final velocity equation. One point to note is the j component will obviously be the part that's changing in this case because of gravity, and that will be the part that impacts on where the particle reaches its highest point or where it may actually hit the ground again.